So we saw how to add and subtract vectors, so what we're going to look at today is a kind of multiplication. There isn't a true multiplication of vectors, but there is what's called a dot product. So a dot product is simply going to be a single number calculated between two vectors. So if you give me two vectors, I can give you what's called the dot product between those two vectors. So it's just a single number. And we'll use it for some different applications as we go forth. So the way we can find this dot product is if we're given two vectors. Let's say we're given vector A is A1 comma A2. So just an X and a Y component like we've seen. And vector B is equal to B1 comma B2. So X component and Y component of B. Then the dot product we write as this. We write it as A with kind of a big solid dot in the middle with B. So this is called usually A dot B. Is simply equal to A1 times B1 plus A2 times B2. So we multiply the X components and we multiply the Y components and we add those together. So if we look at this first one where we're trying to find A dot B, we have these two vectors. I can write them in the bracket form if I'd like. So A is going to be -4 and 6, and B is going to be 7 and 8. So in this first one, I'm doing A dot B. All I'm going to do is I'm going to multiply the first one, so -4 times 7. So those are the first things in the vectors, plus 6 times 8. So that's -28 plus 48. So that's going to give me a dot product of 20. Now, ironically, if I do B dot A, it's basically the same thing. I'm just going to start with the different vector. I'm going to start with the B vector. So that's going to be 7 times -4 plus 6 times 8. That's -28 plus 48 still, so that's still 20. So it's just a quick way you can see that A dot B equals B dot A. So we say that vector dot products are commutative. You could also do a vector dot product amongst itself. You can do A dot A. So A dot A, I would just take the first vector, which is 4 times 4, because both vectors are A. And actually, they're negative in this case, so -4 and -4. Plus the B or the Y components of those, which is going to be 6 and 6. So -4 and -4 is 16. 6 times 6 is 36, so that is 52. The last thing you see here, which we'll use in this section, is the double line of A. And remember the double lines, this means the magnitude. And the magnitude is just simply how long the vector is. So I'm doing the magnitude of vector A. Well, we know its components are -4, 6. So it's some vector that looks like this. So I can just use Pythagorean theorem to find the magnitude. So I know the magnitude of this squared is going to equal -4 squared plus 6 squared. So that is going to say the magnitude is going to equal the square root of 52. Because 16 and 36 is 52. And then I just take the square root of it. So pretty straightforward how dot products work. We want to look at a couple of different applications of what we can do with these dot products. One is we can actually find the vector or the angle between two vectors. So if you think about two vectors in the coordinate plane, let's say I have one going this way and one going up this way. There's some angle in between those two vectors. And so there is a formula to find the angle between these two vectors. The formula is cosine of theta equals u dot v over the magnitude of u and the magnitude of v. So this is, if we're doing two vectors u and v, the top is my dot product, and my bottom is my individual magnitudes. So basically how long each vector is. So if I look at the example here, we have two vectors. We have A and B. A is vector -4, 6. So -4, 6, which is the one we had before. Oh, it looks somewhere like there. So there's that vector. There's vector A. Vector B is 7, 8, which would point up in this direction. And so we're trying to find the angle between these two vectors. So we're trying to basically find this angle theta here. Well, we know that the cosine of this angle is going to equal A dot B over the individual magnitude of A times the individual magnitude of B. Well, first let's go ahead and find A dot B. A dot B is going to be -4 times 7 plus 6 times 8. It's the same one we found before. That's -28 and 48, so that's going to be 20. The individual magnitude of A we did before as well, because again, it's a little right triangle with one side of -4 and one side of 6. So it is the square root of -4 squared plus 6 squared, which is the square root of 52. And vector B, which is dealing with this right triangle over here, the magnitude of vector B is going to be the square root, and again, it's going to just be those two sides squared, 7 squared and 8 squared. So 7 squared and 8 squared is 113, so square root of 113. So now we know the cosine of theta equals the dot product, which is 20, over the two magnitudes multiplied together. So it's 20 times radical 52 over 113. And if I multiply those together, that's 20 over the square root of 5,876. So that's not our angle, that's the cosine of the angle. So like we've done several times, when you want the angle and you have the ratio, we'll take the inverse cosine. So we're going to find what's the inverse cosine of 20 over radical 5876. So if I put that in my calculator, I get approximately 78.9 degrees. So this angle theta is about 80 degrees, and if you look at it, it's a little less than 90, so I would believe that. Okay, there are two special kinds of relationships between vectors that we can look at, and those are what are called parallel and orthogonal vectors. Parallel vectors are just going to be two vectors going the same direction. So two vectors going the same direction means they have the same angle. And kind of a really neat thing about that, they always will have a dot product of 1. So instead of actually finding the whole angle and making sure they have the same angle, we know they always go the same direction if they have a dot product of 1. So as long as we know the dot product, we can know whether they are parallel. Now an orthogonal vector, same kind of idea. It's going to be two vectors that meet at a 90-degree angle. And the way you can see that, they always have a dot product of 0. So if you have orthogonal vectors, they always have a dot product of 0. So 1 is going to be parallel and 0 is going to be orthogonal. So the parallel vector is 1 this way and then 1 the same exact way. And then orthogonal, just like it would sound, two vectors that go at opposite directions meet at a 90 at their tails. Okay, let's go ahead and check out a couple of these. And we want to determine if the vectors are parallel, orthogonal, or neither. And so just remember, if the dot product is 1, then they're parallel. If the dot product is 0, they're orthogonal. And if the dot product is not 1 or 0, then it's not orthogonal or not parallel. It's just something else. So really to do this, all you have to really do is find the dot products. So this first one, I'll find u dot k, which is going to be -1 times 2 plus -6 times -1. That's going to be -2 plus 6, which is going to be 4. And I really don't care about anything else because in this problem we just want to know if they are parallel or orthogonal. And so this is neither parallel or orthogonal. You could find the angle using the formula we did before and figure out what it is. It turns out the angle between them is about 72, 73 degrees. But in our case, we don't care because it's not 0 or 1. So let's look at vectors A and B here. So if I do A dot B, that's going to be 7 times -2 plus 2 times 7. So if I look at that dot product, I get -14 plus 14, which is 0. So a dot product of 0 means they are orthogonal. So the vectors are orthogonal. So if I wanted to graph them on this big grid I have down here, just for fun. So I have 7, 2. 7, 2 is a vector that would look something like this. And -2, 7. -2 and 7 up would look something like this. And I would believe that looks like a 90, so I would believe those are orthogonal. Finally, we have S equals 8, 2 and T equals 4, 1. So if I wanted to sketch those just to kind of see what's going on, we have 8, 2, which is here, and 4, 1, which is here. So if I'm going to guess those are parallel, but let's do the dot product. So this is S dot T. So that's 8 times 4 plus 2 times 1. And when I divide that by its individual magnitudes, that's going to be the square root of 68 times the square root of 17. So that will turn out to be 34 over 34, which is our 1. And so since it's a 1, I know these are parallel. All right, the last application I want to show you is one from physics, and it's about what's called work. Now, work is how much energy, so it's the amount of energy that you need to use to move an object some certain kind of distance, okay? So we can do this actually using a dot product. So if we're given a force vector, and we'll call this F with our little vector on top, and a displacement vector, and we'll call this D, then I can actually find the work between those two vectors. The work between those is just the force vector dot product with the displacement vector. So the force is how much somebody is pulling or pushing or something like that. And then the displacement vector is which way is it going. Am I dragging a rock up a hill? Am I pushing it along a smooth road? That would be your displacement vector. So we'll look at a couple examples here. So we have in this first one a wagon being pulled horizontally, exerting a force of 60 pounds on the handle at an angle of 25 degrees to horizontal. How much work is done moving the wagon 50 feet? So we have to find out these two vectors, the force vector and the displacement vector. So let's go ahead and draw our very sleek wagon here with our handle. Now our handle is 25 degrees from the ground, and I'm pulling this handle with 60 pounds of force. So our force vector is going at kind of this angle at a force of 60. So if I want to find my force vector, I have a x and a y component. I really need to find out what is that x and y component. Well, if I think about this triangle that's formed with this wagon, it has a hypotenuse of 60, an angle of 25, and then it's going to have some x distance here and this y distance here. And that x and y is really what's going to make up our components. So we know that the sine of 25 is y over 60, and we know the cosine of 25 is x over 60. So the y component is going to be 60 sine 25, and the x component is going to be 60 cosine 25. So 60 cosine 25 is the x component, and I could certainly get a decimal approximation of that if I wanted, but I'll just put it in there for now. And then this is 60 sine 25. Now, as far as our displacement vector, we're trying to just move this wagon 50 feet. We'll just say 50 feet this way. So that's actually a really, really easy vector, because the displacement vector is just simply going to be 50 feet horizontally, but I'm not moving it up any, so it's just going to be 0. So, same idea. Now we have these two vectors. Now to find the work that's attributed between those. So how much work is done, how much energy is used by pushing this wagon or pulling this wagon 50 feet. Well, I'll do the dot product, which is going to be 60 cosine 25 times 50, plus the second vector is going to be 60 sine 25. But the nice thing here is it's times 0. And so since it's times 0, we really don't care. So the work that's going to be done is going to be 3,000 cosine 25. And the unit for this, since we're pulling at a certain pounds of force and we're going a certain distance, our energy is going to be in foot-pounds. So there is a conversion from foot-pounds to a more common energy unit such as joules, but foot-pounds is a pretty typical one that you will see in kind of physics work problems. So we set up these two vectors and we just simply took the dot product, and you get the work between done pulling this wagon a certain distance. So let's look at the last one. Nothing much different here. So a person's pulling a freight cart. So we have a freight cart being pulled with a force of 53 pounds at an angle of 20 degrees. And we're trying to make it go 20 feet. So our displacement vector, again, is just going to be 20, 0, because we're just moving it straight along the ground. You certainly can move it up like, say, a ramp or something, but in this case, we're just not doing that. And then our force vector, similar to above, we're going to take the magnitude. Not sure why I put a degree there. It's 53 pounds. So it's going to be 53. Remember, the x is always going to be cosine, and the y is always going to be sine. So when I find the work between those, it's going to be 20 times 53 cosine 20 plus 0 times, who cares, because it's going to go away, 53 sine 20. So that is simply going to be 1,060, because 20 times 53, cosine 20, and again our unit's going to be in foot-pounds. So angle between the two vectors, work, are the two pretty important, pretty useful applications from dot product in beginning trig. When you get to calc, there's a lot more applications, but for now, just some pretty simple ones. Hopefully it's pretty straightforward, but if you do have questions, obviously, please let me know.